This is lesson 1.6, and this is actually the printed version of the attachment for the textbook for this section. So I want you to be aware of the resources that you have, and do make sure you at least click on that to get your free point for this Math Excel assignment. So our topic today is absolute value equations and inequalities. So our goal today would be able to interpret complicated expressions by viewing one or more of their parts as a single entity, as well as to create equations and inequalities in one variable and use them to solve problems. My main goal is to kind of briefly go over this, and then you know that if you would like more information, you can go more in depth and spend a little bit more time on the extra examples. So I'm going to kind of skip over this section right here, straight on into just our refresher on the definition of absolute value. So absolute values, remember, are a number's actual distance from 0 on the number line. In other words, absolute values are always positive. So you can see the absolute value of 4 is 4, but the absolute value of negative 4 is also positive 4. In the same way, the absolute value of x equals x as long as x is greater than or equal to 0. So that makes sense. Positive 3 equals 3. 10 equals 10. As long as it's positive, or 0 equals 0. But once it becomes negative, if we put a negative value in here, like the negative 4, negative 10, absolute value of, if x is less than 0, then the value of the x inside is going to be negative, or the opposite of x. So looking here then at the number line, you can see that's just the visual of what we were talking about above, that absolute value is defined as a number's distance from 0. Next, we have a couple of examples. So example 1, problem 1, you can see the goal is what is the solution to the absolute value of 2x minus 1 equals 5. So taking this step by step, so you're absolutely welcome to print this out and do the same. Absolute value of 2x minus 1 equals 5 is actually going to create for us two different scenarios. The one where we know the value of this equals positive 5, and then the other one where we're going to set it equal to the opposite. So that happens right here. You can see both equations are represented where we set it equal to 5. The left side stays the same when we drop the absolute values, but the right side is where we make 5 into a negative 5. Solving each one of those, adding the 1, 2x equals 6, so we know divide by 2, x will be 3. And then we also have on this other equation here, adding the 1 and then dividing by the 2, x equals negative 2. Both, so you can see or is written there, so we have both would be solutions. So we could check it's always good to check, and that's actually really important for these types of questions. So 2 times negative 3, or positive 3, sorry, 2 times 3 minus 1, we take the absolute value, we get 6 minus 1, so that's 5, absolute value of 5 is indeed 5. Over here, you've got the 2 times the negative 2, which is negative 4 minus 1. So that absolute value is going to be the absolute value of negative 5, which also equals a positive 5. Both of those solutions work. It's not always the case. Here's another problem for us. This one adds an extra step. So the key to notice here, you noticed up here, the only thing on the left side was the absolute value expression. That's what we need to happen here in order to drop the absolute value symbols and create those two equations. So in order to do that, we would just add the 1 to both sides and then divide both sides by 3. So you can see here we're going to add the 1 to both sides. Now we have a 9. The 1 is now gone. Divide the both sides by 3, and the absolute value of x plus 2 equals 3. Now we can split into the two situations. One where it just equals the positive 3. We just drop the absolute value symbols. And then the other one where we drop the absolute value symbols and set it equal to negative 3. So you can see it's kind of nice. They go step by step. finally, we just solve both equations and we have our solution. Now, again, we need to check. So you can see when we plug in 1, everything works out. When we plug in -5, that becomes a +3 times 3 is 9 minus 1 works out. So far, so good. It all works out. This part right here is really important to notice because it has possibly a new phrase for us, extraneous solution. So if we ever have a situation where it works out that we wind up with the absolute value of some number or expression equals a negative, that doesn't work. That's not possible. And so when that happens, we call those solutions extraneous, which means that they aren't actually solutions. It doesn't actually work out. If we plugged a -5 in for x, the result would be a +5. So this is just never true, kind of like we've talked about in previous lessons. So here's where we check for extraneous solutions. We have 3x plus 2 absolute value is equal to 4x plus 5. Everything's already on to the right-hand side. Only thing on the left is absolute values. That's good. Drop them. This is going to be left alone. And over here, this is the first time we've had more than just a monomial. We have 2 terms here. So we have to make the whole thing negative. And so that's going to turn out like this. -4x minus 5 when we distribute the negative. Add the 4x to both sides, subtract the 7 from both sides, and we get 7x equals -7. And then here are our 2 solutions. But now it's time to check. So when we plug things in, -3 into both sides, you can see here we have the absolute value of -7. We know that that equals 7. But when we plug in -3 on the right-hand side, it says -7. So that's not true. That's never true. And so that's called the extraneous solution there. Over on the right-hand side, the -1, everything worked out. So your only solution in this case would be x equals the -1 because the -3 is an extraneous solution. This next thought relates back to our lesson for 1.5. So the solution of the absolute value inequality, absolute value of x less than 5, include values greater than -5 and less than 5. So here we're switching from an equal sign in an equation to an inequality. Major shift here. It creates a compound inequality. Lesson 1.5. You'll notice when there's a less than symbol, the word and will be used. Less than. I think of the word and, than, less than, add a D. Less than. That's when we use and. Greater, that'll be the other way. We'll use an or, but let's focus on the less than first, and let's try one out. So we have, what is the solution of the absolute value of 2x minus 1 is less than 5. Right here we split. We have -5. What is done here actually is the 2 expressions are combined into one. So we've got the 2x minus 1 is less than 5, and we also have the 2x minus 1 is greater than -5. So that's one way to write a compound inequality. Another way to write that would just be to say, okay, well, 2x minus 1 is less than 5, and 2x minus 1 is greater than -5, and solve both of those alongside one another. So here you would add 1 here as well as here. So you can notice from one step to the next we've added 1 to each part. And then in the last step we've divided each part by 2. If it helps, you're welcome to do it this way, adding 1, dividing by 2, x is less than 3. And then over here, adding 1, 2x is greater than negative 4, dividing by 2, x is greater than negative 2. And indicates we could combine it all into 1 and say, okay, well, x is less than 3, greater than negative 2. And you can see that demonstrated on the number line here. Greater than negative 2, less than negative 3. The overlap just happens in between those two values, and both are open circles. Next up, the last type of example is where we have OR, the absolute value expression where we have the symbol greater than or equal to. So that's going to be a case where we're going to use the phrase or the word OR. Great or, that's how I remember that one. Great or than. So walking through this question, we create our two inequalities. A key thing to note here, when we have 2x plus 4 is less than or equal to negative 6, we've taken the opposite, and that means we flip the symbol. Over here we have just dropping the inequality symbols, and we have this inequality here. Next, we're solving each inequality side by side, so subtracting the 4 from each side gives us negative 10, dividing by 2 gives us negative 5. And over here, subtracting the 4 gives us 2x greater than or equal to 2, dividing by the 2 then gives us x greater than or equal to 1. Again, this is an OR situation. X is less than or equal to negative 5, goes this direction. X is greater than or equal to 1, goes this direction. But the values in each one of these ranges is a solution to the original inequality. In summary, we have this table here that can remind us the absolute value of x equals a. That's going to give us 2 points on a number line, or 2 solutions, up to 2 solutions, where we set our x equal to the negative a as well as x equal to the a. Then we have the absolute value of x is less than a, or less than or equal to. Both have the same, move in the same direction in that we would use an and. So and is used with less than. Then with the greater than or greater than equal to symbols, that's when we use or. So here's the overlap with the and the or has arrows going in different directions. They could both be going in the same direction as well, but it would include all of the possible values represented. Here's one real-life situation, car racing. In car racing, a car must meet specific dimensions to enter a race. Officials use a template to ensure these specifications are met. What absolute value inequality describes heights of the model of race car shown within the indicated tolerance? So you can see here the heights, possible heights, 52, greatest allowable height is 53, least allowable height is 51. So we have the tolerance would be the difference divided by 2, so the tolerance would be 1. And then we could find that defining h for the height of the car, and we would subtract the 52, we would get between 1 and negative 1. We could be an inch above or an inch below in order to include that additional element there. So as an absolute value inequality, you could write that as the absolute value of h minus 52 has to be less than or equal to 1. So there's an expression that just demonstrates absolute values in the context of a real-life scenario.